Okay, so welcome back to the third days of our conference school. And it's a pleasure to introduce again Anna Fino, who is going to give the second lecture on interplays of complex and symplectic geometry.
Yes, thank you very much. Good morning to everybody. So before to talk about symplectic Labiau problem, I want to finish the last part of the previous lecture. And I want to give to present some results related to bismuth-Keller-like condition. So the idea is we work again with an Hermitian manifold. We consider the bismuth connection that was the unique Hermitian connection whose torsion is Q-symmetric in all the arguments. And the idea here is, okay, we cannot first that the bismuth connection does not satisfy the first Bianchi identity. In fact, if we take the cyclic sum of the curvature B over, we do the cyclic sum over X, Y, and zeta, we can note that this is not zero. In fact, there are terms in terms of the differential of the torsion and the nabla B of the torsion. And one can ask when nabla B satisfy the same condition for the curvature of the Levi-Civita connection in case of Keller geometry. And this is exactly what we will consider. So we will say that the bismuth connection is Keller-like if satisfy the first Bianchi identity. So this cyclic sum is 0 and the tie condition, right? So RB, if you change X and Y with X and JY, you get the same. That's exactly the property of the curvature of the Levi-Civita connection. And was conjectured by Angela, Luis Utal, Antonio Tal, Luis Ugarte, and Raquel Villacampa, that if you have an Hermitian manifold, the bismuth connection, and the bismuth connection is Keller-like, then automatically the metric G is pluriclose. Pluriclose metric we introduced in the first lecture. And this conjecture was shown, there is a preprint on arXiv, shown by Zhao and Zheng. In fact, they show that the bismuth connection is Keller-like if and only if G is pluriclose. So remember that was the condition that omega, the fundamental form, is D bar close, and plus the condition that TB, the torsion, is parallel with respect to the bismuth connection. They proved that using some local unitary frame, let's say, adapted to the Czech connection. I think it would be nice to have a proof, a direct proof, without using that local frame. And what we did with Nicoletta Tardini first is to see, okay, last time we introduced a pluriclose flow, I show again that the pluriclose flow is preserving the pluriclose condition. So a natural question is to see is also preserving the Keller-like condition. And we will see that for complex surface, we have a nice behavior. Okay, for complex surfaces, so for n equal to 2, the situation is more simple because the torsion of the bismuth connection is just minus star of the Lie form that we introduced in the first lecture. And in fact, to be Keller-like, bismuth Keller-like, is related to the Weismann condition for the metric on complex surfaces. Remember that I will recall the definition of Weismann metric. Hermitian metric on a complex manifold is a Weismann metric if you have simply this relation. So the differential, I did something wrong. Okay, the differential of the fundamental form, omega, is equal to theta, which is a D close 1, 4, but in fact is the Lie form, okay? Theta wedge omega, with the property, with the extra property that the Lie form is parallel with respect to the Lie-Civita connection. In particular, from definition, one can see the Weismann metric argudution, so in particular pluriclose.
Hola,
Yes.
hola, buenas, ¿me escuchas? No te escucho. Hola.
There is maybe someone with the microphone on, or there is someone that wants to ask some question.
Ah, es verdad.
Okay, no, I think it's some people talking. Okay, anyway, I don't have to touch up, sorry. Anyway, if let's do like that, so I stop, okay. If the metric is Weismann, then one can show also the property that the norm of theta of the Lie form is constant. And what we show with Nicoletta is that for a complex surfaces, the condition to be Weismann is in fact equivalent for the metric to be pluriclose and ably satisfy the first Bianchi identity, right? Which is exactly the condition to be, let's say, Kerr-like, equivalent to the condition to be Kerr-like by the theorem that we saw before. And then we try to understand what is going on with the pluriclose. If you start with a Weismann metric, what happened? We didn't success to prove that a pluriclose flow preserves in general the Weismann condition. Maybe that's true, but it's open. We assume this extra condition that's as the scalar curvature is constant. In fact, this is equivalent to ask that the Chern connection is also scalar curvature constant. And then in this case, we show that the pluriclose preserve the Weismann condition. This condition to have a constant scalar curvature is in some sense related to the Kähler-Kohn, because this say that the Kähler-Kohn is K-semi-stable in the Collins sense. So it's an extra property related to the Kähler-Kohn. It would be great, it would be nice to remove, in fact, this assumption, but this we don't know, is not clear. How we prove that? We prove essentially that the Ricci form of the Chern connection can be written like H differential of J theta, where theta is the Lie form for a C infinity function. And the assumption for the scalar curvature to be constant is equivalent exactly to ask that H is constant. And then in such case, you have the first Chern class of your complex surfaces is 0, and one can get, in fact, the result quite explicitly. Another case where we consider in the first lecture, and we are able to prove that the pluriclose flow preserve the Bismuth-Kähler-like condition is the important case. That's, I think, curious, because if you are in an important six-dimensional groups and with an invariant complex structure, and this means a Bismuth-Kähler-like metric, let's say in the sense that I wrote before, then you have some restriction on the complex structure, because the complex structure has to be abelian. This was a condition that I already considered, and was the case that if you take the 1,0 part of the Lie, of the complexification of the Lie algebra G, then this is abelian. This is actually that condition. And we show that, in fact, the pluriclose flow is preserving such condition on two-step nilpotent groups. So maybe it's true in general, it would be nice to have some general result for that. Okay, now we can start really the second lecture and talk about symplectic Calabi-Yau problem. So here's nice, very nice lecture by Wiesen. He already introduced the Calabi-Yau problem, theorem, and so on. So we will see in the context of symplectic case. So the idea is that we will consider an almost complex structure instead of a complex structure. So Mj will be the Ninoyos tensor will be non-zero, and we already saw in the first lecture the notion of tail. Remember that was essentially that the 1-1 part of omega was positive. Now I recall the definition of calibrated or compatible symplectic form with J. Here we ask that both the condition to be tail plus the condition that omega is of type 1-1, is J invariant. Okay. In the case when J is not integrable, this is the usual notion of almost scalar structure. And of course, when J is integrable, you just have the Keller case. Okay, this was already introduced more or less by Wiesen. And so let's consider first the Keller case. So let's take a Keller structure. And let's take this C omega that essentially is a point of the Keller cone, okay? So the difference between omega, big omega, and small omega is an exact form, which is also the DC clause. So by DDC lemma or DD bar lemma, which is the same things, one can write the element of C omega in this way. So the difference is DDC exact, so can be written in this way. And remember that in the Keller case, the Ricci is J invariant. And we have that in fact, the Ricci form is closed and represents the first chain class. So the Yau theorem just says essentially that if you take a compact Keller manifold and you take a closed 1-1 form, which represent the first chain class, then there exists a unique Keller form in the class of omega that I defined before, such that the neuro tilde is the Ricci form of the complex manifold, let's say. In the literature, there were many results, great interest in extending Yau theorem to non-Keller setting. Here we will see the essentially in the symplectic case. So Mj will be non-zero. And the motivation to extend that comes from writing the symplectic version of the Calabi-Yau theorem that we saw again in the lecture by there is again some people talking. Okay, so let's see the symplectic version. So the idea is to interpret the previous theorem in terms of volume form. So we have again a compact Keller manifold in the volume form, and we ask, I will always use the term normalized volume form. It means that the integral of the volume form associated to omega, and the new volume form is essentially the same. Then, by Yau theorem, there exists a unique Keller form in the same class, the starting Keller form, such that you have essentially that the volume associated to the new Keller form coincide with the normalized volume sigma. And okay, the new omega tilde can be write, of course, as positive function, so a function of the form exponential of f times omega. So you can write it in this way, essentially. This is the same equation, right in this way. And you are in the same cohomology class, but you are still of type 1-1, still J invariant, okay, the exact form, the alpha. Yau, essentially the idea of Yau is to solve the associated complex Monge-Ampère equation which can be written in this way. Okay, here we apply exactly the DDC lemma and show that always have a unique solution. The way how we show is to use continuity method. So instead of considering F, essentially what he did is to consider TF plus a constant depending by T, okay? Doing this change, you consider the new equation, and then by continuity method, essentially look for T in the closed interval 0, 1, for which you have the solution, and show that this set is in fact open and closed, okay? The openness by implicit theorem, and the closer by the a priori bound. That's the more difficult part. And I will go back to this case later for this priori bound. Okay, so one can formulate, first thing, one can formulate the same problem, removing the condition to be Kähler and asking only to be compact, almost Kähler. So we write the same problem. So we have a compact almost Kähler manifold with, let's say, normalized volume 4, this condition. And then we write let's say, the Calabi-Yau equation of before in these terms. These are exactly the condition for the volume. The alpha J invariant is the same. And I put this extra condition, this star alpha equal to 0, if we want alpha to be unique. Okay, in general, you have only the uniqueness of the alpha. Here we can see a difference between n equal to 2 and then bigger than 2, because for n equal to 2, the system is not overdetermined, but it is overdetermined for n bigger than 2. And for n equal to 2, the nice thing of this, let's say, system of equation is the solution are unique. Of course, one can ask when you have solution, and this is what we will see in this lecture, but I will give now the proof why for n equal to 2, the problem, the equation has a unique solution, is a nice proof by Donaldson, very simple, not using analysis at all, just geometry. And the idea is the following. So suppose that we have 2 solutions of the symplectic Yau problem. Okay, then now the volume form should be the same, right? So the wedge of omega 1 2 times is equal to the wedge of omega 2 times. And then we can write omega 2 again, like omega 1 plus an exact form. This is exactly the condition that comes from this equality, okay? And this is a tricky, because now we can take just the sum of the 2 symplectic form, omega 1 and omega 2, and what we get is still a symplectic form, which is of type 1 with respect to J, that's fixed, and define a Riemannian metric, GT. And then what we have, that this equation, you can write like, let's say, the new symplectic form, wedge the alpha equal to 0, but that means that our omega bar, let's say, is type 1 with respect to J, and it is primitive with respect to this, let's say, the fundamental form associated to GT. But that means that it is self-dual, okay? So the star, not this, but the alpha, sorry, of course. I will see, I'm writing something wrong. So it means the star, the alpha, is equal to the alpha, but that means that if you by using Stokes, that if you integrate the alpha wedge the alpha, you get 0, and then the alpha is 0. So the proof is very simple. And in fact, this is the problem that I wrote is related to a more general conjecture by Donaldson that said if you take a compact symplectic or manifold with an almost complex structure tamed by the symplectic form and the normalized volume form, sigma, in the sense that I wrote before. If you take a symplectic form in the class of omega, which is calibrated by J, and solve the Calabi-Yau equation, then there are infinity a priori bounds on this new symplectic form, which depend only on the original symplectic form, on an almost complex structure J, and on the volume form, normalized volume form. This conjecture is quite important because as some straight application like symplectic Calabi-Yau children holds for compact almost scalar for manifold with B plus equal to 1. I will say more about that, the case B plus of 4 manifold equal to 1. And as a consequence, if B plus is 1 and there exists a symplectic form timing J, then there is a new symplectic form calibrated by J. One can remove this assumption and look more general about this question posed by Donaldson, and is the following. The question is, suppose that J is an almost complex structure on your compact form manifold. If J is tamed by a symplectic form, is there a symplectic form compatible with J? Again, here the situation is different from n equal to 2 and then bigger than 2, because for n equal to 2, we are, the question is true locally for all almost complex form manifold. And this, the proof of this is was done, I think, by Rivière and Tian. And there is a nice new proof in the paper by me that I mentioned now for higher dimensional example. In fact, this is not anymore true for n bigger than 2. There are examples. I think the first example were constructed by Adriano Tomassini and are on Iwasawa manifold, as far as I remember correctly. And then there are other more general results, like the nice result by Leimi, where it shows that if you take J such that is define a nearly scalar structure, that means the nabla x, J x is 0, okay, that condition, then J cannot be calibrated by any symplectic form. Here, nabla, of course, is the nabla or Levi-Civita. So you have this condition. And then there is more recently another result by Luigi Verzini, where he proved that if you take a almost Hermitian structure for which you have a connection, Hermitian connection with torsion, which is Q-symmetric, cannot be calibrated by any symplectic form. Okay, so here we have a big difference between, let's say, complex dimension 2, a higher complex dimension, and but anyway, the relation between tame and compatibility is also interesting in higher dimension. There are many. There is a rich literature about that, for instance, by Tomassini, Hind, B and Zhang. There is some question.
Okay, yes.
B plus, sorry, I didn't tell. Sorry. So B plus, let's go back. So essentially, let's say it's a dimension of harmonic form, which are also self-dual, okay? So, or you can think in another way, taking the working on H to MR and see the number of positive eigenvalues of the intersection pairing. That's equivalent. I hope that I answered the question. Okay. Okay, good. Sorry. Okay, so that's Donaldson question. is confirmed essentially when M is equal to CP2, and the first proof was given by Gromov, essentially showing that the symplectic form on CP2 is essentially the standard one, the standard symplectic form. And then later there is another proof by Taubes, and he proved that using pseudo-holomorphic curves. And then we saw already that the J integral, this is true, okay, for complete dimension 2, that was in the first solve. And let's go to this result by Taubes that almost solved the problem, in fact, for B plus equal to 1, because if you take a compact symplectic form manifold with B plus equal
Maria,
to,
dimmi tutto.
and you take a generic omega tame, almost complex structure on M, is compatible with a symplectic form, omega tilde. Okay, what I mean here for generic means that if you take the Fréchet space of omega tame, almost complex structure, it means that is an open and dense subset. It proved not only that, it proved a nice property for the new symplectic form in H2, because it can be taken in the same class of omega if this one, the class of omega, comes from a rational class. How he constructed this new symplectic form is a very nice, is a long paper, very nice result, because what he did is start with the class, let's say here, no, this, we take this class, the class of omega tilde, and then inside this class, he constructed a current, a closed 1,1 positive current T, which is in the same class, and the current T that in the literature is also called tau current is constructed by integrated over essentially pseudo-holomorphic curves. He put some extra condition on this torsion that makes the fact that essentially you don't take all the possible omega tame, almost complex structure, but just an open and dense. That's for the condition of T that is a little bit technical, and I will not write here. But more recently, I saw that in the archive, there is a paper by Peng, Tang, Wang, and Zhao, where you see it's still on archive, it's not published, where it seems that they removed, they generalized the Taubes result, removing the condition to be generic, working on essentially on Taubes current and generalize the result. Okay, so let's see, let's go to the existence of solution for our symplectic Calabi-Yau problem, and let's see what is known about sufficient condition for the existence of solution. There is a first result by Van Kopf that essentially say if the Ninoyos tensor is small, okay, small in the sense with respect to the norm L1, then you can B plus is 1, then the symplectic Calabi-Yau problem has a solution. This epsilon that control the norm of the Ninoyos tensor is depending only on the metric G and on the norm of F. F is a function in the Calabi-Yau problem. One have another condition by Tosatti, Vainkov, and Yau that is involving the Chern connection. Let's say that is a sort of sectional curvature associated to the Chern connection. Here I use the index with respect to a local unitary frame, and you see that is modified by something involving the Ninoyos tensor. Anyway, if this curvature quantity is bigger than or equal to 0, then the symplectic Calabi-Yau problem can be solved. This condition, this is in fact shown also in higher dimension. In general, the only known example where you can apply this condition is, let's say, a small deformation of Fubini study matrix structure on the complex projective space. But already for a simple example, like the Kodaira-Thurston surfaces or manifold that we consider in the first lecture, one cannot apply the existing result that I saw before. So here I just, in the first lecture, this nil free was H in that notation. So it's just the real Heisenberg group. Okay, so let's take the same manifold that I considered in the first lecture. Here we just write explicitly a frame, a global frame, because in fact we have the nil free times R is essentially diffeomorphic to a copy of R4. So we have the global coordinate x, y, zeta, t. And it turns out that the first three are close, and D4 is equal to E1 wedge E2. And I will simply use this notation to say what I say. So the first three 1 form are close, and D4 is equal to E1 wedge E2. What is nice from geometric point of view, that the Kodaira-Thurston surfaces can be viewed as a T2 bundle over T2. And one, of course, have many family of symplectic form. If we consider this one, the simple one, E1 wedge 4 plus E2 wedge 3, one can see that this one is Lagrangian with respect to the previous fibration. So it means that it's vanishing on the fiber, all right? The fiber corresponds exactly to the previous coordinate, zeta and t, let's say, and x and y are the coordinate on the base. I will denote in a different way the base 2 torus with the fiber 2 torus. And the first result about Kodaira-Thurston surfaces was shown by Tosatti-Vankov, and they showed that the Calabi-Yau equation can be solved for every T2 invariant volume form. So we have not every volume form, but we have this extra assumption on the normalized volume form, and we ask that it is T2 invariant. And the idea of the proof, the argument of the proof, is essentially, again, using solving problem. And to solve the problem, they essentially write the things in order to reduce everything to a priori bound on the metric, okay, associated to the, let's say, to the new symplectic form. And they show that, in fact, the trace of the new metric with respect to G is less than equal to the minimum over the Kodaira-Thurston surfaces of the Laplacian on F. And then they use the continuity method to get the result. Okay, here I will see that, in fact, this case can be reduced in an equivalent way in a motion pair equation, which is real, not any more complex, like in the case of Calabi-Yau problem, original one. So the trick is the following. So consider alpha. Okay, if you are in the killer case, you can forget about this part because you just know that your d alpha can be written in terms of ddc of a function. Here we use this tricky. So we just consider alpha equal to dv minus v1. And then the nice thing, the Calabi-Yau problem that we have can be written essentially in this type of equation. This type of equation is essentially of this form, is the determinant of, let's say, identity plus the Hessian of V, okay, equal to exponential of F. And here we can apply a general result that was shown by Yang Li, that the Riemann-Champer equation on the standard torus, so not only T2, is more general. In fact, you can consider instead of phi, you can consider a symmetric matrix S. The important thing here that S plus Hessian has to be positive. This is the important condition. But anyway, the Riemann-Champer equation of the previous form can always, as always, a solution. So one can prove in another way the result before by Tosatti and Ivankov. And the idea was, in fact, that was not only one single case, but the result was more general. One can show that, in fact, one can generalize this argument to other almost scalar structure on T2 bundle over T2. The structure of T2 bundle over T2 is quite rich. In fact, they are geometric for manifold in the sense of torsion. What does mean for geometric for manifold is a pair. So you have an X, which is a simply connected Riemannian for manifold. And then you have a group G of isometry acting transitively on X. In fact, you can assume that X, G is the identity component of. There is another question. Okay, no, Filippo answered. Okay. So I will go on. G, in fact, what I was saying, that is identity component of group of isometry, but such that, so you have this action, transitivity action on X, such that contain a discrete group, gamma, such that the quotient has finite volume. Okay. There is a nice result by Uwe, where he classifies essentially what are the orientable T2 bundle over T2. He showed that is a geometric for manifold, and he's also say what are the X, the possible X. One is R4, nil-free cross R that we already see. The other, the potently group in dimension, real dimension 4, with structure equation are given by that. And then the solvable case, which is solve-free cross R. And you see that here, in these two cases, the group is quite restrictive. Is not the case of these other two examples. And in fact, this is what is called in the literature to be an infrasolve manifold. That means essentially a smooth quotient covered by a solve manifold. So if it's finite covered by a solve manifold, because here what happened that essentially you have a quotient like X over gamma. Gamma is not a subgroup of X in general, but contain a lattice such that the quotient is finite. Okay, so if gamma coincides with gamma tilde, then you have what I call in the first lecture a compass or manifold. And then what we consider is some invariance for the almost scalar structure. That means that is induced from a left invariant structure on X, and is also gamma invariant. And what we show, the first thing that we show with Yang Li, Simon Salomon, and Bezzoni is the Tosatti-Ivankov-Yau condition is satisfied only if you are in the killer case. So essentially, it's not the case that we want. And then I go to the result. We show that, in fact, this is in two papers. The first paper is in the Lagrangian case, and the second one in the non-Lagrangian case. We show that if we take a T2 bundle over T2 with an invariant almost scalar structure, as I said before, then for every normalized volume 4, which is T2 invariant, then the problem has a unique solution. So the idea, we use the classification, we describe the invariant Lagrangian almost scalar structure, but the interesting thing that again here, the problem reduced to a real Riemann-Champer equation, and we show that such equation is the solution. I skip the description here of the T2 bundle over T2. are in the slides. And I go to the real Monge-Ampère equation. Here I didn't write all the condition on the case. So what we get is some equation like that, but there is some symmetry here because when this part doesn't appear, then you have exactly the Lagrangian case, and for D non-zero, constant D, these are all constants satisfying special condition that comes essentially by the fact that the equation is in fact elliptic. And for D non-zero, we have a non-Lagrangian case because in some case the fibration can be Lagrangian, in some other case the fibration can be non-Lagrangian. Okay, so the way essentially we show the result is there's essentially to find a priori estimate. We found a Chi2 priori estimate. Here I would say here and also later, all the data are infinity. So if you find the existence of Chi2 solution, then it's fine. Okay, because automatically you have also C-infinity solution. Okay, but still we have this T2 invariant volume. Another way, another generalization that we did later is to consider only S1 invariant volume 4. So the idea is to think again, this is the Kodaira torso surfaces, but instead of looking at as a T2 bundle over T2, we look now as S1 bundle over T3. So the coordinate over the fiber is zeta, right? And X and Y and T are the coordinate on the base. So in this case, the base is T3. And what we show, we did this for this type of symplectic form, but in fact it can be done for other symplectic form. This is not a problem. And we show that the Calabi-Yau equation has a unique solution for every S1 invariant volume form. This is exactly the normalized condition. So the integral of the exponential of f, v, volume form, the standard volume form on the free torus is 1. How we show that? This is the first step. You can see that the trick is very similar to the one that we use for the special case, because we write down alpha, again, like DCU, that's the things that you do for the usual Calabi-Yau, here minus U1, okay? Then, okay, we use, yes? Oh, there is a question.
Okay, there is a question now.
A question about the symplectic Calabi-Yau equation. Is this equivalent in the almost scalar case to describing the Chern-Ricci form? I think is not equivalent, but there are some relation because also the Chern, the prescribing the Chern-Ricci form, there are results, I think, but they are described, I think, in terms of, as far as I remember, of complex Monge-Ampère equation in the integrable case. I don't know if there is something on non-integrable case. I don't know about that, okay? I think for the integrable case there are that, but I don't know about that in the, I think it's an interesting question to think a little bit that. If there is some result, I think maybe it's in some paper by Valentino, so maybe Valentino is the right person to ask that, but I will look more about that. Yes. Okay, so here with this tricky, we reduce the equation to this equation. I didn't want to do that, sorry. I wanted to use the laser, in fact, okay. This equation, which is fully nonlinear PDE on the three-dimensional free torus. It looks not so complicated, but in fact was not so simple to find a solution. I don't want to show the whole proof, but I want just to show a part of the stuff, which is this part. Okay, of course, we will need first a C0 priori estimate, and then going on until a C2 priori estimate. And in fact, to get a C2 priori estimate, we will find first a C2 row holder priori estimate, right? That's quite standard. But one of the, let's say, one of the priori estimate that we get is this one. Okay. If you look this expression, so this is the gradient. Okay. Essentially the gradient. And if you look this, and you forget about that, this part, this is a little bit different because it should be -1 minus AF, I think, and here the factor is the same. But this is essentially the inequality that was used by Yao to solve the usual Calabi conjecture, Calabi-Yau problem, right? So the difference that we have this extra term, and this is not surprising that we have these extra terms, because come from the fact that we have here this extra term, okay? So we as I say, we first found a C0 priori estimate, which is essentially this one. And then, so the norm C0 of U is less than or equal to a constant depending on the norm of F. And then we got some estimate involving the Laplacian of U and the norm. That's the things now that we need, the C1 exit. And then, as I say, the older C2 row estimate. And for that, we use the result by Tosatti, Wang, Lykov, and Yang. Here for 0, here, I just mean that the integral of the function U over the free torus is 0. That condition comes from the normalization, okay? And I want to finish in the last minutes. So here we apply the continuity method with an alternative proof of this result that was shown by Tosatti, Lykov, and it's quite nice because in fact, they use that is enough to find an L infinity bound to show the result. So they found a way to simplify the proof of the theory estimate. And what they use is a modification of the usual Alexandrov-Backelmann-Pucci estimate, with roughly speaking, just saying, if you take the infimum of a function on a bounded, let's say, domain, then you can control this infimum by the infimum of the function on the boundary and the integral of the Hessian, the terminal of the Hessian, over a set P that in the case of Alexandrov-Backelmann-Pucci is where essentially the function is convex, okay? Here, what Tosatti Lykov used is a modification of that was proved by Székely, and is the following. So let's take R between 0 less than equal than 1, and let's take a smooth function which satisfies this inequality. So you have a control of if with respect to the inf on the boundary, okay, for some epsilon positive, and then you can show a control of the terminal of Hessian, okay? You can show that epsilon power n is less than equal than C0 integral over P of the terminal of the Hessian. And here is the difference between the usual Alexandrov-Backelmann-Pucci estimate, because P, you can see from here, is not the set where the function is convex, but is a set where, roughly speaking, you have a smaller derivative of your function V. And then you just modify a little bit the stuff. You modify your function U with this new function, And then simply using the proposition before, you can get this inequality, is essentially that the determinant of tension is controlled on the right and on the left for a uniform constant. And then you have that essentially you get an L infinity bound of U. So they generalize a little bit our result, more in general. In fact, they consider just an invariant almost compensation inducing the standard metric, the metric for which the frame U1, U4 is orthonormal. But now I finish. Let's go back to the general problem here. I think was later. Okay, it doesn't matter. We still have this assumption as one invariant. In fact, we remove also this assumption as one invariant. We success to write an equation. In fact, we reduce all the problem to a PDE on essentially the Heisenberg. That's the R part. But we don't know how to show that, in fact, our equation a solution in this case, because the theory about PDE on Heisenberg group is there is not much known. There are many problems. There are some nice results using just operator. Let's say this operator in terms of the coordinate, but we will need something about the other operator, adding also the terms involving zeta, okay? And this we don't know. We don't know, I mean, the theory here is missing. Probably if something can be proven in this direction, we can solve the problem, removing all the assumption the volume form, and this would be nice because it's one case where you can always solve the symplectic Calabi-Yau problem. And I think I finish here. Thank you very much. This time I didn't go over time. And thank you very much for the attention. And
thank you, Anna.
There was some question.
Can you hear me, Anna?
Yes.
Okay, thank you very much. So I think I postponed this question because it was not related to what you are saying exactly, but it was more general. And this is a question by Chung Min Pan, who asked, in general dimension, is there any result?
In general dimension, so you mean n bigger than 2.
Yes.
Okay, the problem with n bigger than 2, that as I say, can be overdetermined. There is one result that was the one that I mentioned by, where was, I go back? By Yau, exactly. For instance, this result here, it's also for n bigger, n bigger also of 2. But as I say, and this is something that the people doesn't know, this apply for small deformation of the Fubini study metric or structure on CPN, let's say, but it's not clear if there are other examples where you can apply that. There are, I think there is a paper by Luigi Vezzoni where he consider a little bit more general. We consider the case T2 bundle over T2. And as far as I remember, instead of considering T2 bundle over T2, he tried to consider higher torus, dimensional torus here. And he has some solution. But let's say for this problem, the more interesting case, I think is n equal to 2. Because in this case, we know that for sure the solutions are unique by Donaldson result. And we don't know if it's always the case that you have solution. It's still open, this case. Even the case B2 plus 1, okay, I saw that there is this paper on arXiv, the generalized Taub's paper, but I don't know, now it's 2 years, I don't know if it's published or not. I check and it's not published, so I don't know. It's very long paper, again, like 1,000 paper, and in all the paper, they at the end, they try to remove this, to generalize this Taub's result. I don't know if it's, of course, if the result is published, then will be great, because at least in that case will be solved the problem. There is other question?
Yeah, there is another one.
Okay, could you please explain again what is the significance of the B plus hypothesis in some of the results you mentioned? Yes, essentially it's related, is all the stuff for B plus 1. It's here, I will come. Is essentially this Donaldson conjecture here. Okay, is related to this, let's say the interest for that comes originally from this conjecture, because if was true that conjecture, then automatically B plus 1 were a case where you were sure that the symplectic Calabi-Yau theorem holds. So the people is convinced that for B plus equal to 1, the symplectic Calabi-Yau theorem holds. And in fact, probably is right, because Taus goes almost near, because he showed that for generic almost complete structure. And it seems now that there is this new paper, not yet published, where they show that. So that's why they consider B plus 1 as extra hypothesis. I hope that I answered to the question. Okay.
So, other questions, comments? So if not, let's